Okay, so we have two more examples. So let us look at these examples quickly. So now I assume everyone knows again how to run that first search on the given directed graph. So I'm going to just say, okay, after running depth first search on this given graph, this is what the SCC stack is going to look like. Okay, let me make sure I'm running, saving this video. Yes. Okay, so this is how the SCC stack is going to look like after running depth first search. Again, you may need to run more than one instance if needed on this given directed graph to visit all the vertices. So this is the SCC stack now. So what we now do is the second step. So for that we need to reverse the directions of the edges, which is like this, and now run depth first search starting from the vertex that is in the top of this SCC stack, which is vertex 1. So from vertex 1 we can now start depth first search. So in this case we push vertex 1 and then visit one of its outgoing neighbors, say the 3 or 4. So let us break the type by the lower ID. So go to vertex 3, so push vertex 3 to the stack, that's second vertex we pushed, and then from 3 you can go to 2. So you push 2 to the stack as third vertex to be pushed. From 2 you have a back edge to 1 and can't go anywhere else. So pop out vertex 2, so back to 3. You can't go anywhere else from 3, so back to pop out 3 and back to 1. Now from 1 we can go to 4. So 1 is still in the stack, push 4 to the stack, and from 4 you can go to 6. Again, this edge is going to be called a forward edge because 3 has been already pushed and popped out. So from 4 we can go to 6, that's the fifth vertex to be pushed to the stack. So you have 1, 4 and 6 now in the stack. Now from 6 you can go to 5, that's the sixth vertex to be pushed. Now from 5 you can go to 8, that's the seventh vertex to be pushed. And from 8 we can go to 7, that's the eighth vertex to be pushed. Now from 7 you cannot go anywhere else to new vertex because 5 is already in the stack, so like a back edge. So you pop out 7, now the top of stack is 8. This edge to 6 will be a back edge because 6 is still in the stack. So we cannot go anywhere else from 8, which is time to pop out. So 8 is the fourth vertex to be popped out. Back to 5, we cannot go anywhere else from 5. So we pop out 5, so that is the fifth vertex to be popped out. Then back to 6, we cannot go anywhere else from 6, so pop out 6, that's the sixth vertex to be popped out. Back to 4, can't go anywhere else, pop out 7, and then back to 1, pop out 1. So that means in this instance of that first search, it started from 1 and we are really able to visit all the vertices. We are able to visit 3, 2 and then again back to 1, then 4, 6, 5, 8 and 7. So that means all the 8 vertices are forming one strongly connected component. Okay. So we don't need any other any more instance of that first search. We're able to visit all the vertices starting from 1. So that's the end of this step. So just put together all the 8 vertices, they are one strongly connected component. And you can always cross check. From 1 we can go to 2, 3. So now this is the given graph. Okay, so you have to show the final strongly connected components on the given graph. So on the given graph, so from 1 to 2, 1 to 3, then to 4, then to 5, 6, then to 8. From 5 you can also go to 7. So from 1, I just showed you can visit all the vertices. Similarly, say from 4 you can go to 1, then from 1 to 2, 1 to 3, then 4 to 5, 5 to 7, 5 to 6, 5 to 8. So from 4 you can again go to all the vertices. So you can cross check from each vertex. You should be able to visit all the other vertices. Say from 7 you can go to 8, from there you can go to 5, from there you can go to 6, from there you can go to 4, from there to 1, and then to 2, and then to 3. So you see, from any vertex you can reach any other vertex. So they all form one strongly connected component. Now let us go through one more example. So again, you run depth first search on the given graph and build this SCC stack. So this is now the SCC stack. Now reverse the directions of the edges. So this is the reverse graph. Start depth first search from the vertex that's in the top of the SCC stack, so that is vertex 7. So you push vertex 7 to the stack. Now you see you cannot go anywhere else from 7, so you pop out vertex 7. So you that's the only vertex you're able to visit. So 7 is on its own strongly connected component. So you remove 7 and its associated edges. So this is now the new reverse graph, and 7 is also removed from the SCC stack. So now the top of the SCC stack is 5. So start depth first search from 5. So from 5 you push vertex 5, but you cannot go anywhere else from 5, so pop out vertex 5 also. So 5 is said to be on its own strongly connected component. So after remove vertex 5 and its associated edges, this is what you're going to be left with, and the top of the stack after 5 is going to be 1. So I did not remove them from the SCC stack, but we are already gone. So 1 is now the top of the SCC stack. So you push and pop vertex 1, and you cannot go anywhere else because of that you pop out vertex 1. So 1 is on its own strongly connected component, and you remove 1 and its associated edges. This is what you're going to be left with. So after 1 is removed from the SCC stack, you're going to have 4 at the top of the SCC stack. So push vertex 4 to the regular stack and try to go somewhere else. You cannot do that. So pop out vertex 4 right away. So vertex 4 is gone, and it's on its own strongly connected component. And then you're going to be left with just 6, 3, 2. And again, each joint is on its own strongly connected component. So basically, in this directed graph, we observe that each vertex is on its own strongly connected component. I cannot add any other vertex to a given set and make them reachable to each other. Now, if you look at this graph, there's one interesting thing on this given directed graph. This directed graph is a directed acyclic graph. We worked out this example in the earlier topic on directed acyclic graph. So this is the property for a directed acyclic graph. Okay, each vertex should be on its own strongly connected component. Now, why is that? By definition, a directed acyclic graph should not have a cycle, right? So if you want to have a strongly connected component of size more than 1, that means by definition of a strongly connected component, the vertices that are part of strongly connected component should be reachable to each other, which means there should be a cycle in a strongly connected component. Look at the earlier examples that we have gone through. The best case to take up is this one. So when I say 1, 2, 4, 7 form a strongly connected component, there's obviously a cycle. You can go from 1 to 2, 2 to 7, 7 to 1. That's a cycle. So in order for the vertices to be reachable to each other in a strongly connected component, you got to have a cycle or one or more cycles. So then if you have a cycle, you cannot call the directed graph as a directed acyclic graph. So that's why if the given directed graph has a cycle, you are going to have a strongly connected component of size more than 1, like this. And that directed graph, of course, is not a DAC, it's not a directed acyclic graph. On the other hand, if the given directed graph is a directed acyclic graph, you are going to have each vertex on its own strongly connected component, like we just had in the last example. So you see the contradicting thing. So you can't have both. That means you cannot have a directed graph which is also a directed acyclic graph as well as has strongly connected component of size more than 1. So if the directed graph is a directed acyclic graph, you're going to have each vertex on its own strongly connected component. So there's no strongly connected component in a directed acyclic graph of size more than 1. On the other hand, if a directed graph has a cycle, you are guaranteed to have at least one strongly connected component of size more than 1. And of course, that's not a DAG then. Okay, so this is how all the three are related to each other. Just the directed graph, and then a directed acyclic graph, and then strongly connected components. So again, this could be a complete question in an exam. I could give you a directed graph and ask you to check if it's a directed acyclic graph. If it's a data acyclic graph, I could ask you to write the topological sort of the vertices. You all know how to do that. If the data graph is not a data acyclic graph, then I will ask you to find all the strongly connected components, or just find the largest strongly connected component. That means, of course, you don't know what is the largest strongly connected component right away. So you have to basically find all the strongly connected component and then tell me what is the largest among those. So like in this case, this data graph is not a DAG. So it is guaranteed to have a strongly connected component of size more than 1. So run the process that we went through for finding all the strongly connected components of the given data graph. And after you find all the strongly connected components, you then say the largest among all the strongly connected components is 1, 2, 4, 7. Because we can say what is the size of a strongly connected component. So in this case, the size of this strongly connected component is 4. On the other hand, the size of this strongly connected component is 1. This one is also of size 1, and so on. Okay. So that could be a complete question. So let me save this. You can ask any question. You can type in the